Students, to IIT PAL problem solving session on probability. This is lecture number 1. So, in this session, in 6 lectures, we shall solve many difficult problems involving probability. Since this is a problem solving session, we shall not focus much on the theory. I assume that you are already familiar with the theory, and if you are not, then I will suggest you to go to IIT PAL series of lectures and listen to the lectures on probability, or you go back to your textbooks to revise the basic concepts of probability. However, in these lectures I shall touch upon the most fundamental aspects of probability, so that you can understand what is going on. So, let us start. When we talk about probability, we look at random experiments. So, what is a random experiment? A random experiment can be characterized as follows. It can be carried out any number of times under the identical condition. If these experiments the possible set of outcomes is known, but the outcome of any individual trial is unknown till it is executed. For example, tossing a coin, we know that the possible set of outcomes is T and H, that is tail and head, but until the outcome of a toss comes out, we do not know whether it is going to be a head or a tail. Similarly, throwing a die, the possible set of outcomes is 1, 2, 3, 4, 5, 6. Because if you throw a die, the outcome is going to be one of these 6 numbers, but we do not know which one will come until we throw the die and see the result. Tossing a coin three times and noting the sequence of outcomes. So, the set of possible outcomes is all three are heads, head, head, then a tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 and then a head and tail, tail, tail. As you know, there can be 8 different sequences, because there are 2 possible outcomes for each trial, and therefore, we get 2 cube, that is 8, to be the set of possible outcomes. Notation: this set of possible outcomes is denoted as omega or S, and this is called the sample space. Okay. So, with that background, let us solve one problem. So, the random experiment that we are describing which is as follows: pick a number from the set 1, 2, 3, 4, 5, 6 at random without replacement. Without replacement means if you take out a number from this set, you do not put it back into the set. Now, if the number picked is a prime number, then stop, else you pick a second number. That means, again you are picking from the set of which one element has already gone. Therefore, from the rest of the 5 numbers you pick a second number. If it is a prime, you stop, or if the 2 numbers picked are both even, then stop, else pick a third number. That means, now there are only 4 elements in the set, because one has already been picked in the first attempt, one has already been picked in the second attempt. Now, out of the remaining 4 you pick a third number. So, this is the random experiment. The problem is construct the sample space. How to solve this problem? So, let us attempt that. Since initially there are 6 numbers, in the first attempt we can choose any one of them. So, if I start from here, let me write first attempt, and what are the possible outcomes? 1, 2, 3, 4, 5 and 6. What our experiment says? It says that if it is a prime, then we stop there. Therefore, we stop at this point. If we get a 2, if we get a 3, or if we get a 5. In these 3 cases, our output is only one digit, namely 2 or 3 or 5. Now, if I get a 1 or 4 or 6, we go for the second pick. So, if we have got 1 in the second attempt, what we can get? We can get any of the remaining 5, and therefore, we can draw the graph like this. It can be a 2, 3, 4, 5, 6. If we have got a 4, then in the second attempt we can get 1, 2, 3, 5 or 6, and if we get a 6, then in the third attempt we can get 1, 2, 3, 4 and 5. Now, let us go back to the experiment. It says that if this is a prime, then we stop, or if the two numbers that we have picked up both are even, then we stop, else we continue for the third attempt. So, let us look at when we stop. So, this is where we stop, this is where we stop, and this is where we stop. Therefore, in these cases the outcomes are 1, 2, 1, 3, 1, 5. So, let me circle them. Similarly, from here we stop at 2, we stop at 3, we stop at 5, because these are prime numbers, and also we stop at 6 because the two numbers that have been picked are even. Therefore, what are the outcomes so far? We get 4, 2, 4, 3, 4, 5, 4, 6, and let me circle them. And similarly, for the third case, we stop if we get 6 2, 6 3, 6 4 and 6 5. As per the rule of the experiment, we stop. So, in the remaining cases, we now proceed to pick the third number, and suppose we got this 1 4, then from 1 4 we can get 2 3 5 and 6. From 1 6 we get 2 3 4 and 5. From 4 1 we get 2 3 5 and 6, and from 6 1 we get 2 3 4 and 5. So, how many sample points are there? One length we have 2 3 5, length of 2 we have 1 2 3 4 5 6 7 8 9 10 11, and in this case we have 4 plus 4 plus 4 plus 4, that means 16. So, total 30. I am not doing it, but you can easily understand the point here is going to be 1 4 2, 1 4 3, etc., and like that you can compute the entire set of 30 possible outcomes that we can get for this random experiment. Let us solve another problem. The random experiment is as follows. Suppose in a bus stop there are 4 passengers. Each passenger may have 1, 2 or no bags. That means this is 0. You come to the bus stop and pick up 1 or 2 or 3 or 4 passengers and each passenger takes his or her bags. Describe the sample space as a pair of numbers, number of passengers and number of bags. So, your sample space are made of points of this nature. There are two components, one is the number of passengers you picked and the number of bags you picked. So, question is describe the sample space. How to proceed? So, in a very similar way, you start from here. Number of passengers may be 1, 2, 3 or 4. If the number of passenger is 1, the number of bags that you might pick is 0, 1 or 2. Therefore, the points belonging to the omega is equal to 1 0, 1 1, 1 2. Now, suppose you pick up 2 passengers. How many bags then you may have to pick? It may be 0, it may be 1, when one of them has 1 bag, it may be 2, one may have 0 bag, other may have 2 bags, or both of them have 1 bag each, 3 or 4. Therefore, the corresponding elements in the sample space are 2 0, 2 1, 2 2, 2 3 and 2 4. In a similar way, if we go from 3, we will get 3 0, 3 1 up to 3 6. Therefore, the points are going to be 3 0, 3 1, 3 2, 3 3, 3 4, 3 5 and 3 6, and similarly from 4 you may get 4 0, 4 1, 4 2, 4 3, 4 4, 5 6, 7 and 8. So, total number of points in the sample space, that is the cardinality of omega, is equal to 3 plus 5 plus 7 plus 9 is equal to 24. Now, the question is, why do you need to compute the sample space? This is important because we will later see that we will try to associate probabilities with some subset of the possible outputs, and for that we need what is the size of the subset that we are interested in and what is the total size of the sample space, as we will see later. Therefore, construction of the sample space is very important. Now, so far we have seen that the sample spaces are finite, but it is not necessary that the sample space are going to be always finite. For example, let us consider the following example. You toss a coin repeatedly until you get a head. Count the number of tosses required to get the first head. Describe the sample space. So, number of tosses if it is 1, that means in the first toss you got a head. If it is 2, that means in the first toss you get a tail and that is followed by head. If it is 3, then you get 2 tails followed by a head. If it is n, that means you got first n minus 1 trials, all of them are tails followed by a head, and n can be any positive integer. Therefore, your omega is going to be 1, 2, 3 up to infinity, that is the set of all possible integers, which we know that is infinite. Although it is infinite, it is countable. There may be experiment with uncountable sample space. So, example, suppose we pick a point from the interval 0 to 1. That means, we want to pick up a real number in the interval, in the open interval 0 to 1. How many possible ways of choosing it? The number of possible ways of selection is infinite. But more importantly, it is not countable. I hope you understand the difference between countable or uncountable. So, to make it easy, an infinite set omega is said to be countable if there is a one-to-one mapping between the elements of omega and the set of natural numbers. So, in the earlier example, since the set itself is 1, 2, 3 up to infinity, this natural mapping is existing there anyways. If such a mapping does not exist, then it is uncountable. Why therefore the interval 0 to 1 is uncountable? Because between any two real numbers, say 0.2 and 0.35, again we can have infinitely many possible real numbers. Therefore, we cannot make a one-to-one mapping between the set of positive integers and the omega. Why I mentioned this? Because towards the end of this series of lectures, I shall do some examples where the omega is uncountable, and that is for your knowledge that in such cases how do you compute the probability. Okay. So, let us consider the following random experiments. Suppose we have 10 identical red balls. We need to put them in 3 boxes such that none of the boxes is empty. How many possible ways of putting the balls in the baskets? So, that is the question. Note one, the balls are identical, and 2, none of the boxes will be empty. What is the significance of these two? So, let me first explain that. Suppose we have 3 balls A, B, C. That means we can distinguish between the 3 balls, they are not identical. In how many ways we can put in 2 boxes such that none is empty? That is the question. Therefore, we can do it in the following way: A comma B C, that is one way of arranging; B comma A C, C comma A B, A B comma C, A C comma B, and B C comma A. Therefore, 6 possible ways. But if the balls are identical, then we have only the following possibilities. One in the first box and 2 in the second box, and 2 in the first box and 1 in the second box. There is no other way of arranging this. So, only 2 possible ways. Why? Because none of the box will be empty. Now, if we allow some box to be empty, then in the first case we can have 2 more possibilities. That is A, B, C and 0 in the other one, or 0 and A, B, C. So, total 8 possibilities. In the second case, we can have 3 0 and 0 3 also. Therefore, 4 possibilities. So, I hope you understand the significance of identical balls and distinguishable balls like A, B, C, and also keeping some of the box empty and keeping no box to be empty, that is another variation. Now, our problem is to put 10 balls in 3 boxes such that none of the boxes is empty. So, how to do? So, consider this balls. In among these 10 balls, we have to put some in box 1, some in box 2 and some in box 3. So, how many ways you can do? The solution to the problem is as follows. So, let me start from slightly beginning thing. Suppose there is only one box, then number of possibilities is equal to 1. You put all the balls in the box. Suppose there are 2 boxes, then the possibilities are one in the first box, 9 in the second box, 2 in the first box, 8 in the second box. So, you can easily understand the points are going to be like this. So, how many possibilities are there? It is very easy that there will be 9 possibilities. Now, consider three boxes and none will remain empty. Therefore, in the first box, how many elements can be there? There can be 1, 2, 3, 4, 5, 6, 7. Can we have more than 7 there? No, because we can have 8 also. We can have 8 there, and then the remaining 2 we can put 1, 1. So, there are 8 possibilities for the first box. How many balls are remaining? Now, the remaining number of balls are 9, 8, 7, 6, 5, 4, 3, 2. So, these can be put in two boxes, second and third, in how many ways? It is very easy to calculate that, because when there are 10 boxes, 10 balls, we found that we can put in two boxes in 9 ways. Therefore, when there are 9 balls, we can put it in 8 ways. When there are 8, we can put it in 7 ways, and when there are 2, we can put it in only one way, that is, one in the second box and one in the third box. Therefore, total number of possibilities is equal to 1 plus 2 plus up to 8 is equal to 8 into 8 plus 1 is equal to 9 by 2 is equal to 36 different ways. Now, suppose we have 100 identical balls to be put in 20 different boxes, such that none of them is empty, then it is not possible to go in this way, because at each step, as the number of boxes increased, we have multiple possibilities coming up. So, how to solve it? So, suppose there are n identical balls, which we have taken 10. So, let me draw 10. And we need to put it in 3 boxes. So, what we do? Consider the gap between 2 balls. Suppose I put a vertical line there. That means, I am dividing it into 2 different parts. Suppose arbitrarily I choose 2 such lines. Then I can say in the first box there is 1 ball, in the second box there are 5 balls, in the third box there are 4 balls. So, this leads to the following configuration 1, 5, 4. On the other hand, suppose arbitrarily I choose 2 lines, and these together I will get there are 3 balls in the first box, 2 balls in the second box, and 5 balls in the third box. So, that gives you an idea of how to solve this problem. So, out of 9 gaps, we have to choose 2 to put the vertical line. Therefore, number of solutions is 10 minus 1, choose 3 minus 1 is equal to 9 C 2 is equal to factorial 9 upon factorial 2 into factorial 7 is equal to 8 into 9 by 2 is equal to 36. We get the same answer that we have got before. Therefore, in general, if there are n identical balls to be put in k boxes such that none of the box is empty, then the number of possible ways is equal to n minus 1 c k minus 1. And I have demonstrated how we arrive at this number. So, let us solve a problem based on same principle. In how many ways three positive numbers x, y, z can be chosen such that x plus y plus z is equal to 15. Suppose this is the problem, then we can easily break it into a similar the ball and box problem. So, consider 15 ones. So, we may consider them to be identical ones because they are the same. Now, I have to find out three numbers such that their sum is 15. Already I have 15. So, I can arbitrarily choose two lines in the 14 gaps, and that gives me the partition 2, 8, 5. So, one possible way of arranging them is x is equal to 2, y is equal to 8 and z is equal to 5, and therefore, possible ways is 14 C 2, and you can understand how we got this number. Now, consider the following. We have 10 identical balls to be put in 3 boxes such that any box can remain empty. What is the number of possibilities? That is the question. So, how do we solve it? We have the solution for situation when no box can be empty, but here any box can remain empty also. We do the following. So, along with the n balls, we also add k. So, let me put them in a different color. So, this is the n balls and this is the k boxes. So, we have n plus k many different items. In how many ways n plus k can be distributed into k boxes such that there is no box which is empty. So, n plus k elements can be put in k boxes such that none is empty is n plus k minus 1 C k minus 1, and I claim that that is the number of solutions. Why? Because now we have k partitions, none of them is empty. So, how many balls are there? N plus k balls, right? Subtract 1 from each configuration. Therefore, now we will have n balls in k boxes, but some box can be empty also. So, let me give you a small example. Say 3 balls and 2 boxes. We know that solutions are 0, 3, 1, 2, 2, 1 and 3, 0. So, what we are doing? We are saying that 3 plus 2, that is 5 balls are there, and I am partitioning it into 2 boxes such that none of them is empty. Therefore, what we do? By the earlier problem, out of the 4 gaps, we choose one partition. So, consider this. Therefore, the arrangement of ball is 1, 4. Now, if we subtract 1 from each of them, we get 0, 3. Similarly, if we consider this to be the line, then we will have the solution to be 2, 3. If I subtract 1 from each of them, then we get 1, 2. Now, you understand, since we can choose the partition is in 4 ways, there are 4 different arrangements for the balls. So, I hope that this concept is clear. When the boxes are not allowed to be empty, the number of solution is n minus 1 C k minus 1. When the boxes are allowed to be empty, then the number of solution is n plus k minus 1 C, or choose k minus 1. Okay, friends, I stop here today. I hope you understood the concept. In the next class, I shall start at this point and we shall solve some other problems related to probability. Okay, friends, thank you.